Hi everyone, we're going to work on solving exponential equations today. And as part of your opener, I'm actually going to ask that you try this right now. We don't really have a strategy for this yet, so I'll give you a little hint here. And the hint is to think about what does the exponent need to be, or 2 to the power of what is 16, and see if that can drive you to try to figure out what we need x to be. So think about what the exponent needs to be, and then see if you can't solve from there. So go ahead and hit pause, work through this opener real quick. Should be just a real quick check-in at the very least. Just try something. It does not need to be perfect. After you unpause, how this all worked out, and then we'll jump into the lesson here. Okay, so like I said, for us to figure this out, I'm thinking, what does the exponent need to be? Well, one way for me to kind of work through that is I'm just going to rewrite 16 as 2 to some power, right? And 16 is equal to 2 to the power of 4. So I need x plus 3 to equal 4. If x plus 3 is 4, then we're going to get this to be a true statement, and we'll be able to find the value of x. So then x plus 3 equals 4, I subtract 3, and I get x equals 1. And I can check this, right? If I plug 1 right back in, 1 plus 3 is 4, and like we just found, 2 to the power of 4 is 16. Okay, so this is one way of how we can solve exponential functions. And one thing I just want to point out here is this is exponential when the variable is the exponent. Okay, so when we need to find the exponent as a variable, this is one strategy to do that. And we're going to actually jump into this a little bit further. So when solving exponential equations, there are times that we can get both exponential terms that have the same basis, just like we did in the opener. In this case, we can just set the actual exponents equal to one another and solve. And that's, again, what we just did in the opener here. Okay, so first step, rewrite the equation so that we have the same base. That's really the main thing to take away from here, is that this is the same base. Then set the exponents equal to each other and solve from there. Okay, but getting to that same base is key to all of this. And let's work through this kind of step by step right here. So step one, getting the same base. Well, I can rewrite each of these as a power of 2. So the left side I'm going to leave as is. That's 2 to the power of 3x minus 8, and it's going to equal 2 to the power of what is 16. We just did that in the opener, 2 to the power of 4. So now that the bases are the same, we need 3x minus 8 to equal 4 so that we get these sides to be equal. So step 2 has us taking those exponents, 3x minus 8 equal to 4, and now has us solving. So if I add 8, I get 3x equals 12. If I divide by 3, I get x equals 4. Okay, so x needs to be 4 here, so that way we end up getting 2 to the power of 4 on the left side. Right? If I check this, 3 times 4 is 12, 12 minus 8 is 4, 2 to the power of 4 is 16. Okay, so sometimes it's going to be, I don't want to use the word obvious, but it's going to be, we may only need to change one side of the equation to get that same base. There might be times, though, that we're going to have to take both sides of our equation and try to find the base, like what we see here for number 1. So I'm going to do number 1 here, and I'm going to ask that you all do 2, 3, and 4 and pause the video. But one issue we have here with number 1 is that I can't rewrite 9 as some base to get to 27 and vice versa. So I can't just rewrite one of the sides here. Instead, both sides are going to have to get rewritten. So I'm like, okay, what can I write 27 and 9 as so they have the same base? Well, I know that 9 I can write as 3 squared. So then I'm wondering, can I rewrite 27 as 3 to some exponent? And the answer is yes, right? 27 is equal to 3 cubed. So I'm going to start with that. Instead of 27, this is 3 cubed. That's still to the power of x plus 3. And instead of 9, I'm going to write that as 3 squared, and that's still to the power of x minus 1. Well, now the bases are the same, but I also have this exponent property of an exponent being raised to another exponent. When that's the case, I multiply those exponents. So this exponent of 3 is going to distribute, and this exponent of 2 will also distribute. So I get 3 to the power of 3x plus 9, and it equals 3 to the power of 2x minus 2. Now we have the bases to be the same, and so for me to solve this, I'm going to take each exponent and set equal to one another, and now we're just solving from there. So I'm going to get x's on one side, so I'm going to subtract 2x. That makes this 1x. I'm going to subtract 9. Negative 2 minus 9 is negative 11. So our answer here is negative 11. Okay, so why don't you all hit pause and work through 2, 3, and 4. At the very least, see if you can't identify what that base should be. Again, sometimes you might have to rewrite one of the side of the equation. Sometimes you might have to rewrite both. Sometimes you may not even have to rewrite either side at all. So take a few minutes, work through those. After you unpause, I'll have all the work shown, and we'll move on from there. Excuse me. All right, number 2 here, rewriting 125 as 5 cubed. That then gets us to 5 to the power of 3x minus 6 equals 5 to the power of 3x. Now the bases are the same, so the exponents equal to each other. But when I do that, the x's cancel themselves out, right? When I go to subtract 3x, all the x's go away, leaving us with negative 6 equals 0, which is, there's nothing to solve for, right? That's a false statement, and thus there's no solution. There's no value of x that we can plug in here to get these sides to be the same. Down here on number 8, this is one of those cases where we have to rewrite both bases. I can't rewrite 4 as some or 4 to some power to get 8 and vice versa. So I recognize, though, that 8 and 4 can both be written as a base of 2, 8 being 2 cubed and 4 being 2 squared. Just like we saw in number 1 here, we have that exponent raised to another exponent, so this 3 does distribute. That's how I get the 3x minus 6. This 2 also distributes. That's how I get 2x minus 6. This time, when I set those exponents equal to each other, I subtract 2x, and I get 1x on the left side. But when I add 6 to both sides, that 6's go away. And so I still have an x to solve for, but there's just no number that we end up getting because negative 6 plus 6 is 0. And thus, that brings us to our solution of being 0. Okay, really easy to miss or mix these two up. A lot of students will still think that this is no solution. All right, and last one, number 4, the base here is e. Remember that e, anytime that we see e, we want to be thinking natural logs. Yes, we're not to the log part of this yet, but remember that e is going to show up every time we see that ln. So as a reminder, ln of x is equal to log with the base e of x. Okay, that's completely separate from what we need to do here on number 4. But anytime we see this e, I want us thinking, hey, that's something to do with the natural log. So bases are the same, right? They're just base e. So I just set the exponents equal to each other, and I'm getting x equal negative 13 halves. Okay, if you want to call it negative, would that be 6.5? All the same. Okay, it doesn't really matter. All right. We're not going to always be able to do this, okay? And that's to take both sides of the equation and get to a common base. In fact, most of the time with exponentials, we're not going to be able to do this at all. So we need another strategy, and hence why logs are so important. Logs allow us to solve for exponents. Okay, that's why we spent this whole unit working on understanding what a log is. So many times we're not going to be able to get a common base, and thus we'll have to solve the equation like we do with most other equations where we undo operations to isolate the variable. Part of us undoing the exponent is us taking the log of both sides. Okay, so now we're really getting into what is the purpose behind a log, and the main purpose of it, again, is to be able to solve for the exponent here. So regardless of what form it's in, always a good idea to start is to isolate the exponential term. Okay, and let's back up even more so. Before we even get to that, how is this different from what we were just doing? Well, here I only have one exponential term, right? There's only a 4 to the power of x. There's not a second exponential term, okay, like the 16, okay, where I can rewrite that as an exponent, okay, or number 1, right, 2 exponential terms. So as we start to plan on how to solve, I first am checking, can I rewrite both sides so that I have the same base? This is much harder here because of that 3 and because of that 18. And then if we can't get both sides, excuse me, to get that same base, then our next task is to isolate the exponential expression. Okay, in fact, that's just a good idea of what to do almost always. So what do I mean by that? Well, the exponential expression is the term that has the base and the exponent itself. So I need to get that by itself before I do anything else. So I'm going to subtract 3 from both sides. So that's 4, then x, or 4 to the power of x minus 2, and it equals 15. Well, this is the point where I might be able to say, hey, can I rewrite 15 as a base of 4 or both sides as a different base? In this case, we can't, right? They're their own bases. So I'm like, okay, I can't get a common base. So now for us to solve this, we can either convert this to an exponential. I'm going to show us that in a second. Or, excuse me, and actually, the most proper way to do this, I'm going to back that up. We're going to undo the log by converting it to its exponential. Okay, so let's just say convert to exponential. And this is one of the first things we did with logs, where we take an exponential equation and we convert it into its corresponding log expression. So what that ends up being is log base 4, keep the base the same, and then change the position of the other two terms. So the x minus 2 and the 15 switch. So now it becomes log base 4 of 15, and it equals x minus 2. Okay, so remember log base 4 of 15, that equals a number. I don't know what that number is. It's going to be some decimal. Okay, but now for us to get x by itself, I just need to add 2 to both sides. So our answer in its exact form, we would leave it as this log base 4. It's log base 4 of 15. And I'm going to add 2 to that. And that equals x. Now when I write my answer like this, log base 4 of 15 is its own number. I am not doing log base 4 of 15 and adding 2 to that and taking the log of 17. Those are two very different things. Okay, so keeping the parentheses here is really important. And the reason I have us do this is because this is our exact answer, meaning there's no rounding involved. If we want a rounded answer, we need to actually take and figure out what the value of this log is. Now, I'm going to show us here in a second at the end of this lesson here, you're going to see something called the change of base formula of how we can plug that in to every single calculator. Okay, but for those of you that have, and every calculator is going to be a little bit different. For those of you that have these graphing calculators, we actually are able to change the base to whatever we want. If you press the math button and you scroll up or down, up is going to be quickest, and you find this log base button, that's going to allow us to pick any base we want. So log base 4 of 15, 1.953, and if I add 2 to it, this is my rounded answer. And the reason I say it's rounded, yes, these are decimals and I could write every single one, but it still continues. A calculator does not display every single decimal value. So this ends up being 3.95. We'll say, let's round to 3 decimal places, 3.953. If you don't have this calculator, don't worry. I'm going to show us another way of how we can evaluate that here shortly. For now, I'm okay with just leaving our answers in its exact form. In fact, when you're doing math, exact answers are almost always better than rounded answers. This is our rounded answer. Okay, let's do one more together before we try another one on our own. And you know what? I might even bring in this change of base formula as we get to the final answer so we can kind of see that as well. All right, so back to step 1. Isolate the exponential expression. Remember, that includes the base and the exponent. Everything else we have to undo. So I'm going to add 19 to start. So this is 5 times 7 to the power of x plus 4. After I add 19, 23 plus 19 is 42. Then I need to divide both sides by 5. That's 5 times 7. I can't change that base. The base stays as is. So that's 7 to the power of x plus 4, and it equals 42 fifths. I'm going to leave that as a fraction. So now that I have the exponential expression by itself, or the exponential term, I can now do the conversion into a log. So to do that conversion, I start with log. Base of my exponent is the base of my log, and I change the location of the other two terms. So it becomes log base 7 of 42 fifths, and it equals x plus 4. Now when I subtract 4 from both sides, that's how I get this to be, or to get x by itself and get our simplified answer, or excuse me, exact answer. So 42/5 and then minus 4, and it equals x. And if you want to put parentheses around this whole thing, that is okay. So this is our exact answer. Log base 7 of 42/5 and then minus 4. We're going to try to come up with the actual exact or rounded answer here. And this is where I want us to take a look at this change of base formula and think about how might we be able to do that. So we're going to pause this for a second. And we're going to look at this change of base formula, allowing everybody with a calculator to find the rounded answer here. So sometimes we might want to estimate the actual value of our solutions, like what we were just talking about. Without the use of a fancy calculator, we will have to use what's called the change of base formula to give us decimal answer for this type of problem. So how this works is if I take a log that has a base of b, whatever that might be, it can be anything, of m, I can rewrite that and choose whatever base I want. Usually we're going to choose base 10 because all calculators have logs of base 10. You'll see that it should be easily available on the calculator you're using. Or we could write it as log with the base e, which is the natural log. Again, that's because your calculators have an actual button that's easily accessible for that. So what we end up doing is we take the log, let's take base 10 for example, so log of what I'm taking the log of, so log of m, and divided by log of the base. So I remember that the base goes to the bottom, okay? And again, if I want to take the log, natural log, it does not matter. So a few quick examples here. If I have log base 7 of 13 and I need a calculator to do that, I'm going to use this change of base formula and I'm going to write it as base 10, where it's log of 13, so log of what we're originally taking the log of, divided by log of the base, so log of 7. This is also equal if I took the natural log and made my base e. Okay, these are all going to be the same thing. And now I can do that with my calculator. I can go log of 13. Make sure you close that parentheses so that way it's just taking the log of 13 and then dividing it by the log of 7. Again, close that parenthesis, and I get that to be approximately 1.318. Okay, and I'm just going to show you it's the same thing if I did natural log. So natural log of 13, close that parenthesis, divided by natural log of 7, close the parenthesis, we get the exact same thing. Okay, so this is going to be really helpful so that anybody with a calculator can come up with these values. You don't need a fancy one like me. So let's just do these other two real quick, and then we'll apply that right up here. So this is log of 22 divided by log of 13. Log of 22 divided by log of 13. 1.205. And this last one, let's use natural logs. So this is natural log of -3 divided by natural log of 6. Already seeing an error here because we can't take logs of negatives even when I try to do the change of base formula. It's going to say error as you can't take logs or natural logs of negative numbers. It is a non-real answer. Okay, but if we try to use that change of base formula, that would be our setup there. Okay, so back to number 5. We're working on getting an approximate answer for this, and our problem right now is we don't know what log base 7 of 42/5 is. Well, let's use that change of base formula. So with that change of base formula, this becomes log of my denominator, so log of 7, and the numerator is log of 42/5. And I'm going to subtract 4 from that to get x. So let's do that. Let's go log of 42/5 divided by log of 7, and I get 1.094. Oh, and you know what I forgot to do? I forgot to subtract 4 from that. So that's not our answer quite yet. Let's then press -4, so it takes that previous answer and subtracts 4, and it's -2.906. That's the answer we were looking for. So -2.906. Okay, there's a lot going on. I get it. That's why, again, it's important that right now when I ask you to try, you do your very best and see where you can come up with. Just to kind of give us a hint, start by getting this exponential term all by itself. So you got to do something with that 9 and something with that -2. Go and hit pause, work through this example to the best of your ability. and we'll check our work in just a few minutes. Okay, so let's walk through what we should have done here. You should have started by subtracting 9. That's how I went from negative 43 to negative 52. Then I'm dividing both sides by negative 2. That's how I got this to be 26. At this point, it's where I recognize that the bases are this, or excuse me, the exponential term is isolated, and I can't get the bases to be the same, right? There's no way for me to rewrite 10 and 26 so they have the same base. So I'm going to go ahead and convert this to a log. So this is log base 10 of 26, and now it equals 3x minus 5. Well, log base 10, that's just log, right? I don't need to write base 10. In fact, with it being base 10, I don't need to even do a change of base formula. We have a button on our calculator for this when I go to get my rounded answer. So that's why I just didn't write the base here. So our answer is log of 26 plus 5 and equals 3x. Well, now if I divide both sides by 3, our answer in its exact form is log of 26 plus 5 divided by 3. Let's figure out what it would be as rounded. So log of 26, again, no change of base is needed because of that already being base 10. I'm going to add 5 to that. And I'm going to divide the whole thing by 3, getting our answer to be 2.138. And that is our rounded answer. All right, well, that is basically everything. There is one last problem on the back that's an application. Let's do that real quick. That'll also be part of your homework. And the first thing we're going to have to do is set this up. So it says, what is sustainable, renewable, natural resource when you manage forest properly? Your lumber company has 1,200,000 trees. You plan to harvest 7% of the trees each year. How many years will it take for the harvest to get to half of the trees? So here's kind of a strategy for what we're going to apply to be able to get to our answer here. Okay, we know the number of trees, we know the rate of decay. This also means that we can write an equation or an exponential equation. We're needing to find the number of years to get to half the trees. Well, half the trees, if we start with 1,200,000, is 600,000. Okay, and what we're going to have to do to get there is write the exponential equation, and then we need to use logs to solve this. So remember that exponential equations, any amount is equal to the starting amount, and then 1 plus or minus, depending on if it's growth or decay, that growth rate, and then to the power of t, where t is the number of years. So in this case, we know our starting amount is 1,200,000. Then we're doing 1. Because we're going to decrease, okay, or lose trees, I'm going to subtract the percent, and that percent of 7 I'm going to convert to a decimal. So that's 1 minus 0.07, and now to the power of t. Like we've been doing, I'm going to figure out what that base is. I'm going to simplify it. 1 minus 0.07 is 0.93, and to the power of t. So we have our exponential equation. We now have 2 variables. So the last thing that's missing is how many trees are left after half have been gone or half have been used, and that's 600,000. Well, that's going to plug in to this A right here. So 600 equals 1,200,000, and then 0.93 to the power of t. And now, just like what we've been working on, we need to solve for the exponent. And we're going to start that by getting the exponential term all by itself. All right, why don't you see if you can take it from here. Go ahead and hit pause. I'll have the answer for you in just a moment. Okay. So for us to solve this, again, we need to get that 0.93 to the power of t by itself. So I divide both sides by this 1,200,000. That makes us 1/2, right? 600,000 divided by 1,200,000 is 1/2. So I get 1/2 equals 0.93 to the power of t. It's at this point that I'm like, hey, I need to solve for an exponent. So I'm going to convert that to a log. So it's log of the base is 0.93. And then switch the 1/2 into t, so log of 0.93, or log base 0.93 of 1/2 equals t. Now for us to evaluate this, because we're trying to figure out how many years, so we actually want a rounded answer here, we're going to use that change of base formula. So log of 1/2 divided by log of 0.93, and that's going to tell us the time in years. And again, this is base 10. You could have also used natural log. It does not matter. So log of 0.5 divided by log of 0.93 is 9.55. So to answer the question, we'd say about 9.55 years. That's about how long it would take to get from 1,200,000 trees to about half of them at that decay rate of 7%. Okay, one last thing I'm going to ask you to do is just see how many years it'll take you to harvest half the trees if now instead of 7%, we change this to 5%. So see if you can't build the equation, go from start to finish. With this will actually be posted in the answer key notes. So work through this, check the answer key notes once you're done to make sure you have the right answer here. And then you have a homework assignment that follows. Have a great rest of your day.